Hello, I'm Fakhri and I'm in my second year of my PhD at Glasgow. Today I'll be sharing my projects and showcasing my current stage of progress. My project uses numerical modelling to model the magmatic processes and differentiation in planetesimals. Firstly, what are planetesimals? Planetesimals are the earliest terrestrial planetary bodies in our solar system, accreted from a solar nebula up to a few hundreds of kilometers in diameter. These start off with a primitive chondritic composition similar to the Sun's composition. However, sufficient heating from short-lived radionuclides such as 26 aluminium may cause the interior of planetesimals to melt, mobilize and differentiate into stratified layers. We are developing a first-of-its-kind two-dimensional, multi-phase, multi-component planetesimal model to model the melting and magmatic differentiation in planetesimals. Our model will cover multiple stages of a planetesimal's development. Firstly, we calculate the melting of primitive chondritic rock by using computationally generated phase diagrams. We use the lever rule to calculate the melt fraction at any given composition and pressure-temperature conditions at time. The earliest differentiation may occur at low melt fractions shortly following the onset of melting. When melt forms interconnected networks between solids, melt can percolate through the solid. Denser melts such as core-forming metals migrate downwards through the solid, whereas less dense silicate melts segregate upwards through the solid. This forms an early core and mantle. On the other extreme, at high melt fractions, greater than 50% melt, residual solid grains are suspended in the melt and may rise or sink due to their relative buoyancy. Here, denser particles such as metal solids and immiscible molten metal droplets may form a core via a rainfall mechanism. However, this mechanism may be severely hindered by rigorous convection. But a clustering of these dense particles may also speed the settling, as a cluster would have a higher relative density than the surroundings, driving the flow downwards. So, that's a very brief introduction to the key concepts and fundamental physics of our model. We aim to implement a self-gravitating domain, a free surface tracker, compatible trace element partitioning, and mush flow fluid mechanics for intermediate melt fractions. Thank you for listening, and please contact me for questions.